Okay, let's have a look at question 1, part A. Hydrogen iodide is a colourless gas that can be made from the reaction of hydrogen and iodine. Gives us the equation there, tells us that delta H, the enthalpy of reaction, is minus 9 kilojoules per mole, and the activation energy for the forward reaction is 173 kilojoules per mole. And it's asking us to complete the enthalpy profile diagram for that forward reaction, and it's asking us for 3 specific things to put on that diagram: label the activation energy, label the enthalpy change of the reaction, and include the formulae of the reactants and the products. In terms of the key information in the question, obviously the numbers are important, but not just the size of the numbers, also the signs. So delta H is minus 9 kilojoules per mole. That minus sign is going to be important. It tells us something about the energy change in the reaction. And the activation energy is 173. That's significantly bigger, so we can show that on our diagram. If you've done this question, that's great, carry on. If you've not done this question yet, you might want to pause the video here and have a go. Right, so where are we going to start? We're going to start with our enthalpy of reaction, that is minus 9. That minus sign tells us that the reaction is exothermic. It's not very exothermic, it's a relatively small number, 9, certainly compared to the activation energy, so I'm going to draw a line down here for the energy of our products. Because it's exothermic, we are releasing energy, which means our products will have less energy than our reactants. Drawing our activation energy, a much bigger number, so we've got a big hump to get over, up, and then down to here. So that's our basic diagram. Let's have a look at what we need to label. We've got to label the activation energy, so the easiest way to do that is to draw a line across from here, just a little dotted line, and then our activation energy goes up from where we started to the very peak. And it's important we just put one arrowhead on there, don't put 2 arrowheads, because the activation energy is directional. We are starting here and we are going to here, so the arrow goes up, and we'll label that EA for activation energy. It also asks us to label the enthalpy change of reaction. That is the difference in energy between our reactants and our products. So again, the easiest way to do this is just to draw a little dotted line across there, and then drop a line down from there to there. Again, single-headed arrow. We're going from our reactant to our products, so the arrow is going down, and that is our delta H. Almost finished, but we've got one more thing to do. It's asked us to include the formulae of the reactants and the products. Our reactants are hydrogen gas and iodine gas. I'm just copying these directly from the equation. And our products are 2 moles of hydrogen iodide gas. And there we go, first part done. Things to remember: single-headed arrows only, and just make sure you don't miss anything out. There's 3 things in particular I've asked us to do. Let's just make sure that we've done them all. Moving on to the second part of the question, part B. When the reverse reaction takes place, hydrogen iodide decomposes to form iodine and hydrogen. Calculate the enthalpy change when 336 decimeter cubed of hydrogen iodide measured at room temperature and pressure decomposes, and include the sign for enthalpy change in your answer, and 2 marks for this. So keywords, we're calculating the enthalpy change, and it's asked us to include the sign specifically. Key information, well, we're talking about the reverse reaction to the one that we talked about in part A, and obviously the number is going to be important. The volume of hydrogen iodide is 336 decimeter cubed. We'll be able to use that to work out the number of moles of hydrogen iodide that are reacting. And the other thing that really should sort of put a spark in our mind is this thing here, measured at room temperature and pressure. As soon as you see that phrase, room temperature and pressure, or its shortened version RTP, you should be thinking about the molar volume of a gas. So if you've done this question already, great. If not, you might want to pause the video and have a go at it yourself. So let's have a look at how we answer it. 336 decimeter cubed. We know that at room temperature and pressure, 1 mole has a volume of 24 decimeter cubed. So that is how we're going to work out our moles of HI that are reacting. It is the volume that we've got divided by the molar volume, and that is equal to 14. So we've got 14 moles of HI reacting. Now if we go back to the initial information we're given at the start, we were told that the enthalpy of reaction is minus 9 kilojoules per mole. We just need to be a little bit careful here. When it says kilojoules per mole, it's talking about this equation as written. So it's 1 mole of hydrogen reacting with 1 mole of iodine to make 2 moles of hydrogen iodide. So making 2 moles of hydrogen iodide will release 9 kilojoules per mole. If we're going backwards, so we are reacting the hydrogen iodide, then the sign changes on our enthalpy of reaction. So the enthalpy of the backwards reaction is plus 9 kilojoules per mole. It's endothermic, but that is to decompose 2 moles of HI. So the number we're going to be looking to use in this calculation here is the enthalpy to decompose 1 mole of HI equals plus 4.5 kilojoules per mole. So we change the sign because the reaction is in reverse, and we also have to halve the number because in the original equation we were making 2 moles of HI. So the enthalpy change then is quite straightforward. Enthalpy change is equal to the number of moles of HI that are reacting times the enthalpy per mole, and that equals 63 kilojoules per mole. Things to watch on this question: obviously got to remember to halve the enthalpy of reaction that we are using, so the stoichiometry in that original equation is important, and also be careful with the sign. Just remember that as we're talking about the reverse reaction, the sign will change. Moving on to part C. Part C asks us to calculate the activation energy for the reverse reaction. So command word again is calculate, and it's the activation energy for the reverse reaction that we are looking at. In order to answer this, we have to go back to our energy profile diagram and think about that reverse reaction. What is actually going to happen when we go from our HI to our hydrogen and our iodine? Well, the answer is we have to go all the way over this hump, which means the activation energy for the reverse reaction is the enthalpy of reaction plus the activation energy for the forward reaction. So that's our 9 kilojoules that we've got here plus the 173 kilojoules that we've got here. So once we recognise that, calculation is pretty straightforward. So the activation energy for the reverse reaction is 9 plus 173 equals plus 182 kilojoules per mole. Important to put the sign in there. Moving on to part D, this asks us to calculate, that's our command word, the bond enthalpy for the HI bond in equilibrium 3.1 given the following information, and it gives us bond enthalpies for the hydrogen-hydrogen bond and the iodine-iodine bond. Key information, obviously those numbers are going to be important, and we are looking for the bond enthalpy of the HI bond. And just to help me set out my calculation, I'm going to call that X. That's what I'm going to try and work out. So if you want to pause the video here and have a go yourself, great, otherwise we shall crack on. Now, with these sorts of questions, it's always important to start with the chemical equation. And because that was written on the previous page, I'm going to write it out here again. So we've got H2 plus I2 reversible reaction to HI. And we know that the delta H of that forward reaction is minus 9 kilojoules per mole. That was given to us in part A of the question. With bond enthalpy questions, even though this is quite a simple one, I think it helps just to draw out what bonds we are talking about in our equation. So writing the equation in a slightly different way shows me the bonds. That just makes sure, particularly if we're talking about more complicated examples than this one, that we don't forget any bonds. And then the equation to remember is that the enthalpy of reaction equals the energy to break the bonds in the reactants, so bond breaking, minus the energy released when the bond's in the product's form. So the enthalpy of reaction is bond breaking minus bond making, and in this case we know that is minus 9 kilojoules per mole for the forward reaction. I would always do these in the same way. So we're going to start with the bond breaking. We're going to work out that energy. So what bonds am I breaking? I'm breaking one hydrogen-hydrogen bond, one iodine-iodine bond. So that is quite simply 436 plus 151, and that is 587 kilojoules per mole. Bond making. Now it hasn't given us any information on the HI bond. In fact, that's what we're going to try and work out. So we've said that's going to call it X. We just have to be a little bit careful because we're going to make two of those HI bonds. So the energy involved in making bonds is actually 2X. So I put this number and my 2X into my equation, then I have my enthalpy of reaction minus 9 equals 587 for my bond breaking minus 2X, which if I rearrange that, I get 2X equals 596 by adding 9 to 587, so X equals 298 kilojoules per mole. So my answer is plus 298, and it's always good practice with bond enthalpy, or in fact any enthalpy questions, to always include the sign. If your sign's positive, put a positive. Just make sure that you've thought about it.